This slide returns to the broader SCAL categories and prepares for acoustic and geomechanical topics. It is a good moment to remind students that core analysis is not only about flow and saturation, it also helps us understand elastic and mechanical behavior, which matters for logging, seismic calibration, stimulation, and wellbore stability. This slide is excellent because it shows P-wave velocity measured at different scales: core scale, well-log scale, and seismic scale. Core measurements provide high detail at small scale. Sonic logs provide continuous in-well information. Seismic provides broad aerial coverage at coarser resolution. This is a key lesson in subsurface characterization. Different measurements do not contradict each other, they operate at different scales and must be integrated. Core gives detailed truth, logs provide continuity, and seismic provides field-scale context. This slide shows that in carbonate rocks, P-wave velocity depends strongly on pore size and pore complexity. Two samples may have the same porosity but different pore architectures, and therefore different velocities and permeabilities. This is a very important lesson for students. Porosity alone is often not enough to describe carbonate reservoirs. Carbonates are famous for complex pore systems. An acoustic response can help reveal differences in pore architecture that strongly affect reservoir quality. This slide shows that when all carbonate samples are grouped together, the correlation between VP and permeability is weak. But when samples are grouped by rock type, the correlation becomes much stronger. This is a sophisticated but very valuable point. Rock physics relationships often improve when we compare samples within similar rock types rather than mixing all facies together. In practice, this means lithofacies classification can significantly improve petrophysical prediction. Now we move into elastic properties. Bulk modulus measures resistance to volume change under uniform pressure. Shear modulus measures resistance to shape change under shear stress. These properties are fundamental for understanding how rocks respond mechanically in the subsurface. They matter for seismic interpretation, geomechanics, fracture design, and stress analysis. A stiffer rock generally has higher elastic moduli and deforms less under stress. This slide introduces two more widely used elastic properties. Young's modulus measures stiffness under uniaxial loading. Poisson's ratio measures the tendency of a material to expand laterally when compressed vertically. These are especially important in unconventional reservoir engineering and hydraulic fracturing, where brittleness and deformational behavior strongly influence stimulation efficiency. In general, high Young's modulus indicates stiffness, while Poisson's ratio helps describe deformation style. This slide shows how elastic properties can be used to calculate a brittleness index. The workflow uses Young's modulus and Poisson's ratio, normalizes them, and combines them into a brittleness metric. The result can then be compared with mineral composition-based brittleness. This is useful because brittle rocks often fracture more effectively, which can be beneficial in stimulation design. So petrophysics here directly supports production engineering and completion decisions.